Section 8-4 is on the volume of a solid of revolution by cylindrical shells. The objective of this section is to find the volume of a solid of revolution by slicing into cylindrical shells. If you recall, back in Chapter 5, we learned a technique for finding the volume of a solid, and that method was called the plane slicing method, and we learned the disc method, the washer method, and the slab method were all part of that. And so this is just another way that we can find the volume of a solid, and it depends on the setup for that problem as to which one of these two might be the better technique to use. All right, so let's start out with just an example here. Let's say that we've got a function f of x, and we're going to rotate it around the y-axis. And we're going to do a comparison between these two methods here, the plane slicing method that we already know and this new shell method. All right, so let me just slide this over. And let's say that this is our function here, f of x. And we want to rotate this again around the y-axis. In fact, I'll go ahead and mark that we're rotating around the y-axis. Put a little arrow here to indicate our axis of rotation. And if you recall with the plane slicing method, the way that we did this is we had to draw in our slice perpendicular to our axis of rotation. So if we're drawing it in perpendicular, that means we've got to draw a horizontal slice since our axis of rotation is the y-axis, which is vertical. It's got to be perpendicular to that. So if I draw in my slice here, I can draw a horizontal slice just like that. And the whole idea here was that you drew in one slice that represents all the slices. However, the problem that you run into with this one, you can see that if I drew the slice up here near the top, we'd end up with a different slice. The bottom slice there I can see goes between that vertical line on the right and the curve on the left. Versus at the top, I have it going between the curve on the right and the curve on the left. So it's a different slice. In fact, this value right here, this y value right here, is the key value where it switches between the two. Now I could certainly use that method to find the volume of this thing when I rotate it around the y-axis, but I'd have to split this up into two separate integrals to do it. All right, the bottom slice versus the top slice. So the shell method, on the other hand, says that rather than slicing this thing perpendicular to the axis of rotation, we're going to slice parallel to your axis of rotation. So again, we're rotating around the y-axis, so we'll indicate that. We have the same function here, but we're going to rotate around the y-axis. And so now my slice, when I sketch it in, since my axis of rotation is vertical, my slice is parallel to that, so it's also vertical. So we'll draw in a vertical slice right here. And now you can see that it doesn't matter where I draw that slice, it's always going to go from the curve on the top to the x-axis on the bottom. So with one slice, I represent all the slices there. And so this would be a better technique to use for this particular type of problem because of the fact that I could narrow it down to just one integral that I'd have to deal with. And that's the difference between the two. The only difference is, are you slicing perpendicular to your axis of rotation or parallel to your axis of rotation? If it's perpendicular, that's the plane slicing method, or the disc, washer, and slab method. If it's parallel to your axis of rotation, then it's the shell method. All right, so let's go through and see how we actually use this method here. So let's go through these steps here and just kind of describe the process that we're going to go through to be able to evaluate a volume problem here using the shell method. All right, the first step here, which we just did actually, was to draw a representative slice. And ideally, you draw one slice that represents all of them. In some problems, that's not going to be possible, but for most problems, we're going to see that's the case. In fact, pretty much for all of them, we'll find that's the case. Just like we did with the plane slicing method, we're going to mark the endpoints of our slice in terms of x and y. Depending on whether that slice is horizontal or vertical will depend on whether the x's are the same or the y's are the same, but we'll mark each of those and mark the thickness as well. Again, depending on whether it's lying in the x direction or the y direction, horizontal or vertical, will depend on whether the thickness is a small change in x or dx or a small change in y, dy. And then we're going to rotate the slice around the axis of rotation. And we're going to actually try to sketch what that looks like. Do your best to sketch that. It'll help you in the process if you sketch this out every time. So rotate that slice around your axis of rotation. Now when you rotate it around that axis of rotation, you have a very thin slice that you've rotated around some axis. If you will, think of that slice as being paper thin. In fact, you can even take your piece of paper and do this. When you rotate it around, you're going to literally end up with what looks like a rolled up piece of paper. Okay, it's going to be hollow in the center, and you're just going to have the outside of a cylinder, what we would call the shell of that cylinder. This is why it's called the shell method. Now to find the volume of that shell, again, it's a cylinder, but it's just the outside of that cylinder. Really what we've got to do is find the surface area of this thing, but it is three-dimensional. So the way we do that is by unrolling the slice. We're going to take that rotated slice, and then we're going to unroll it. Take that piece of paper that we rotated around and unroll it. And then you're going to find the volume of your unrolled slice there. By finding the volume of dV, which is the length times the height times the thickness. All right, it's a three-dimensional solid we'll see here in our example. And so the volume of that is just length times width times height, or we're calling this length times width times thickness of that slice. Where the length is the circumference of the rotated slice. Again, if you think about that slice after you've rotated around and then you slice it to open it up, to unroll it, it turns out that the circumference is now the length. All right, and then the last step of this is to integrate dV to find the volume of the solid. So many of these steps sound the same. Of course, the one thing that's different there is the fact that it's a shell, so we have to slice it and unroll it to find the volume of it. But we still come up with dV to represent the volume of one slice, and then through integration we find the volume of the whole thing. All right, so let's take a look at an example that illustrates this for us. In fact, the example is the sketch we started off with here. It says the region under the graph of y equals 4x minus x squared from x equals 0 to x equals 3. Let me write that down. We have y is equal to 4x minus x squared, and that's from x equals 0 to x equals 3. And it says it's rotated about the y-axis to form a solid. So we're going to rotate this thing around the y-axis. I like writing that information down just so it's clear on what I'm starting with in the problem, and hopefully it keeps me going in the right direction there. It says find the volume of the solid by slicing into cylindrical shells. Use fundamental theorem to obtain the exact answer and show that your answer is reasonable. Okay. So let's sketch first of all what this thing looks like here. 4x minus x squared. In fact, it might help if you factor this, just to help you get the sketch of this. Like I said, it's the same sketch we just saw a second ago, but if I factor out an x, I'll have 4 minus x, and x are my two factors there. So that's a function that crosses the x-axis at 0 and 4, where those two factors are equal to 0. So I know where it crosses the x-axis. I should be able to come up with a pretty accurate sketch of this thing, but I am going to rotate around the y-axis, so I want to have enough room here in both the first and second quadrant. So 4x minus x squared is going to look something like this. Okay, and it crosses the x-axis again at 0 and at 4. However, we're only worried about the region from 0 to 3. So that would be, this would be 2. We'll say that right here is 3. Okay, so the only region that we're considering is this region here from 0 to 3. And we're rotating this thing around the y-axis. So I'll go ahead and mark that we're going to rotate around the y-axis. So again, with this shell technique, we slice this thing parallel to your axis of rotation. So I'm going to draw in a slice, say right here. And we're going to go ahead and label the top and bottom point here. I'm going to call this x, y2, and we'll call the bottom one here x, y1. Again, label the endpoints of that slice that you have there. And the x values are the same, the y values are different. And so now when we rotate this thing around the y-axis, we're going to end up with something that looks kind of like this. I'm going to try to sketch it the best I can, and you might want to look at the book there to get a better sketch of what this thing looks like. So that was a little bit too tall. You end up with this three-dimensional solid here. It does actually have a thickness to it when you rotate that around. If you want to draw this in the back there, you can do that too. And so we end up with this three-dimensional shell is what we have here. Again, the center of this thing is hollow. There's nothing in the middle of this thing. It just has this shell. So the technique that we said is I want to take that shell, slice it, and unroll it. So I'm going to draw what this thing looks like unrolled underneath it. So if I were to take this thing, slice it, and unroll it, I'd end up with something that looks like this right here. Okay. Where this height right here corresponds to this height right here. And you'll also notice that when I slice this thing and unroll it, what was the circumference of this thing, that right there has now become the length of this thing. And that's why in our directions there it said where the circumference after you unroll it is now what was the circumference is now the length. All right, so let's write down our dimensions of this thing. And so we have that this height is actually the change in these y values here. So that's y2 minus y1. The length of this thing, again, that used to be the circumference of the original shell. So the circumference I know is 2 pi times my radius, where your radius is this distance. I'll go ahead and mark it up here. This distance right here is my radius. And so the radius of this thing is just the x value. So 2 pi times the radius. So I was going to put that in terms of x, though. And so that's 2 pi times x. Actually, I'll just say that's equal to 2 pi times x. You can leave it in terms of r initially. All right. And then finally, the thickness of this thing. You'll notice that this does have a thickness to it, whatever this thickness right here is, which that's a small change in x. We call that dx. That's the same as the thickness of my slice here. So I'm going to just draw that over here on this side here. I guess this thickness that I see right here, that's the dx. So I have a three-dimensional solid. It's got a length, it's got a width, it's got a height. I want to find the volume of that guy right there. So we call that dv. dv is equal to length times width times height. Or thickness as we put it in our notes there. But dv is equal to our length is the 2 pi times x times the width is going to be the y2 minus y1 times the height or the thickness of this is dx. Again, you'll notice that we're making a differential equation here that we're going to use integration to solve. All right, so now I need to get this in terms of one variable. The fact that my differential there is in terms of x tells me that I want to get rid of the y's, the y1 and y2. So let's go back up to how we defined those. In our sketch, y2 was on the curve up here. So that curve is y equals 4x minus x squared. I can replace y2 with 4x minus x squared. And then minus y1, if you go back to your sketch, y1 falls on, is this point down here that's on the x-axis. That's where y is equal to 0. So y1 is actually 0. So here's our equation then. dv is equal to, let's go ahead and rewrite this actually. dv is equal to, I'll go ahead and distribute the 2 pi x through here. I'll have 8 pi times x squared minus 2 pi times x cubed times dx. And once we have our differential equation in terms of just one variable, we are all set to integrate this thing. Remember, that's the way that we solve a differential equation, is through integration. Of course, on the right side there, we use a definite integral to evaluate this. So let's go back to our sketch and find out what our limits are. Again, notice that my differential is dx there, so I want x values here. And they were nice enough to tell us this actually in the problem. If I go all the way up there, they told us it was going from x equals 0 to 3. And you can even look at your sketch that's how far to the left I want this slice to go and how far I want the slice to go to the right. So I want to go from 0 to 3. Now you can use numerical integration on your calculator to evaluate this, your FNINT, and if you haven't used that in a while, I'd certainly practice it on a few of these. And if you probably haven't used fundamental theorem, which is what they said to use on this one, in a while, so I definitely would practice that on a few of these. So let's integrate this with fundamental theorem here. Integrating dv gives me v, and that's equal to, on the right-hand side there, when we integrate, we'll end up with 8 pi times 1/3 x cubed, and then minus 2 pi times 1/4 x to the 4th. And we're going to evaluate that from 0 to 3, and actually plugging in the 0 is going to be real nice. The 3 is going to be a little bit of work here for us, but we should be able to do that. So we'll end up with 8 pi times 1/3 of 3 cubed minus 2 pi times 1/4 of 3 to the 4th. That's the upper bound. Now again, when you plug in the lower bound, when I plug in 0, I'm going to get 0 cubed there, so that's going to be 0. And when I plug in the 0 to the next term, it's going to be 0 to the 4th. That's going to be 0. So I get 0 at the end. That's why I said that's the nice part. All right, and let's evaluate this then. So I have 1/3 times 3 cubed there. That's 27 is 3 cubed divided by 3, or 1/3 of that is 9. So 9 times 8 is 72 pi minus 3 to the 4th power is 81. And then I've got 2 times 1/4, that's 1/2, so it's 81 over 2, I guess I'll write it that way. 81 over 2 times pi. And again, the 0 at the end drops out. So we have 81 over 2, I guess maybe I should have written that as a fraction just to make, or as a decimal to make that a little bit easier to work with. 81 divided by 2 is actually 40.5 pi. So 72 minus 40.5 pi, that sounds like we're going to end up with 31.5 pi. Okay, there is our definite integral. That is our volume of this solid. Now if you want to double check your answer there, we can go back up to the original, and I mentioned we could use numerical integration. I'm going to just show you to remind you of that, how we do that. So, oops, let me put the original up here so I can see it. Let's move this down. All right, so on our calculator, we'll just punch in that numerical integral there under your math menu. You can find it FNINT. And then punch in our equation, which is the 8 pi times x to the 2nd power minus 2 pi times x to the 3rd power. And our variable is x, that's the second parameter. And then our lower bound is 0, and our upper bound is 3. Those are the 4 parameters we have to specify there. And we can let it crunch a solution there for us. We get 98.960. Again, since this involved pi, you can check to see if this is a nice multiple of pi by dividing by pi. And there, in fact, we get 31.5 pi. That's exactly what we got over here. So that certainly looks like the correct value. All right, that's as far as we're going here in this part of the section.